All right, welcome back, everybody. So today we are working on chapter 6, probably the first two sections of chapter 6. And I call this chapter the linear differential equation. And a lot of people are probably going to be mad at me for saying that because, everybody's going to argue, well, there's all sorts of different kinds of linear differential equations. Why would you say that it's all just one? And the reason why I use this is, or at least the intuition for that, is that all linear differential equations can be rewritten as a Cauchy problem. That's the word we use here, is Cauchy problem, or the name, named after Augustin Cauchy, of course. And we'll talk about how to maybe rewrite differential equations as Cauchy problems eventually, and then we do learn how to solve these. And we know how to solve these, and this is in quotes, theoretically. We're really bad at doing it, actually, according to the theorem, but, that doesn't mean that we can't. But theoretically, we know how to solve all of them. In reality, there's a lot of other things we would rather do than rephrase differential equations as Cauchy problems and solve them in that setting. But theoretically, there's only one linear differential equation, and we're going to learn how to solve it here. So let's just start by talking about linear differential equations. So that's, if we can't approach a differential equation and recognize it as linear, then good luck actually doing anything else with it. So we're gonna focus on just what does it mean to be a linear differential equation, how do we recognize them, etc. So I'm writing it in very abstract form here. It's a functional equation. I'm writing TF equals 0. T is now an operator, and in fact T has to contain at least one differential, because otherwise it's not a differential equation. Okay, so if T contains at least one derivative, and it's linear in the sense that T of f is equal to LF plus g, where you have this additive function g, that's how we'll call it a linear differential equation. So rephrased, using the explicit definition of T, that's really saying that LF plus g equals 0. For a linear differential operator L, that has to be linear as based off of our previous chapter's work and definition of linear. Linear operator, also a differential operator. As long as L is a linear differential operator, f is my input, it's my unknown, and g has been some prescribed function, this is the form that all linear differential equations take. So for example, let's look at this ordinary differential equation, and we see that we have two derivatives, some multiplication, one derivative, some multiplication, and another function. And basically what we're going to do is we're going to reinterpret each derivative. Two derivatives, so I have a second derivative. I have multiplication by 4 cosine. I then have one derivative, and then I have multiplication by 3 e to the t. All of that acts on f. That's my linear operator. And then I have, if I pull sine t squared to the left, I have this additive function, negative sine t squared. And so in defining L as, the linear term, which is acting on f, and g as negative sine t squared, I have exactly, my t equals LF plus g. And so this is a linear differential equation. You could all verify that this operator L is actually linear. So if you want to verify that, go right ahead. But let's move on. We can have linear PDEs as well. So now I have a PDE, and my unknown is this function u. So u is my function here in the PDE, but of course I have a differential operator there, a little bit of multiplication by negative omega squared, and then another differential operator, and then maybe this additive function cosine. Okay, so I'm still just full of linear operators. Both of these are differential in this case, and an additive function. And so we'll go through the same work there. You can define T as the following if you pull everything to the left-hand side. And you can define L as the linear operator, which contains the differentials, and you can define G as the additive function, cosine x minus t. I guess it should have been negative there, but not a big deal. And we recover that we have a linear differential equation. Okay, so exactly. Here's a nice remark from the beginning. Maybe we should always just think about linear differential equations like this, where we have a linear differential operator and an additive function. These are your generic linear differential equations. So in this sense, it's a direct extension of kind of what we were used to when we have the matrix M, the unknown x, and an additive vector b. That's like your linear vector equation, so to speak. This is the same sort of behavior. We have a linear map L, an unknown f, and an additive vector g. So once again, we're just really trying to drill into our minds that differential equations is really just infinite dimensional linear algebra. And it's an extreme subset of that, because we're not, we don't have to work with just generic functional equations, because those could also be infinite dimensional linear algebra, but we're working with just the differential equations in infinite dimensions. So that the operators we care about are only the differential ones here. All right, so that's what we want to do. We want to draw that parallel between mx plus b and lf plus g equals 0. And then we have to use some terms. Okay, so there's a common term that we use to describe linear differential equations, and make sure that you've verified a differential equation is linear before you start applying this term. So that term is called homogeneous. Okay, we want to get used to this term of homogeneous differential equation, because what does it mean? It means that, here's what I'll say. A homogeneous differential equation is my linear differential equation if g is 0. Okay, so I have some generic linear differential equation. There's a linear differential operator on my unknown. I have an additive function. If that additive function is 0, we call it homogeneous. So homogeneous linear differential equations are those that are actually written as the following. A linear differential operator L on my unknown equals 0. So in other words, we can think of homogeneous, and of course, once again, this only applies to linear. So linear homogeneous ODEs as null space linear algebra problems. We're asking ourselves, what is in the null space of L? Homogeneous differential equation says, what is in the null space of my linear operator, my linear differential operator L? That's what homogeneous linear differential equations are. Inhomogeneous is how we describe the equations when that's not held. So if I have the in front of it, we call it inhomogeneous if g is non-zero. So if this is no longer, if g is no longer trivial, if g is no longer 0, then this is a different sort of equation where I'm looking for the differential operator on my function to actually be the opposite of some function g. And so it's no longer a null space problem. It's more like a true inversion problem at that point. And those are going to be important because recall that solutions to mx equals b, my linear vector problems, are x equals m inverse b only if the null space of m is empty. Right? If the null space of M is not empty, then actually I have an infinite number of solutions. And then this idea of an inverse no longer really applies if the null space is not empty, because I don't have an inverse matrix. I have a pseudo inverse matrix, and we have infinitely many solutions because of whatever vectors are sitting in the null space. So we care about homogeneous differential equations because they calculate null spaces for us the same way that null spaces were calculated with matrices. Okay, so that's just providing some motivation for those. Let's look at some examples of homogeneous or inhomogeneous. The following differential equation is homogeneous, right? Homogeneous because I don't see any additive functions here. I only have an f, and the entire term out front is an operator on f. There's no additive g or some other additive function in this linear differential equation. Meanwhile, if I look at the following differential equation, I have my operator out here and my f, but there's a new function maybe on the right-hand side. I could pull it over to the left-hand side, but that function would not be multiplying f. It would be isolated by itself. So inhomogeneous, if I'm not calculating a null space thing, I'm more trying to calculate some sort of inverse of the linear operator. And null space if the right-hand side is 0, as long as I isolate everything with f on the left. Okay, so moving on to section 6.2, we're going to get into these things called Cauchy problems. And I'm adding the term linear in parentheses here because most often when somebody says Cauchy problem, they're going to refer to a linear Cauchy problem, but some people will define nonlinear Cauchy problems. So I should say some mathematicians, and I am actually one of these, allow for a Cauchy problem to describe nonlinear evolution as well. So for now, just assume that when somebody says Cauchy problem, they refer to a linear Cauchy problem, but quite possibly eventually you might get to the point where we are talking about nonlinear Cauchy problems as well. Okay, so I've got a paragraph describing kind of how I started this video, but let's move on to what it means to be a Cauchy problem. A Cauchy problem, in many ways, is an initial value problem. Let's say it like this. Cauchy problem is an initial value problem with only first order, with first order ODE. Okay, so you can't increase your order to, like, 10th order initial value problem, which those exist, right? We've encountered those already. But the Cauchy problem is an initial value problem strictly with a first order ODE, and in fact, it's a little broader than that because the right-hand side is allowed to be an operator. So notice the left-hand side, here's your first order ODE, and then the right-hand side is allowed to be an operator. And this is why you can kind of extend this to PDEs, because if this manages, the L manages to be like a partial differential operator, then all of a sudden you're like focused on PDEs. But for now, we're going to be working in finite dimensional ODEs. So for this course, this is a matrix. Okay. That's kind of something to keep in mind just for this course. For my Cauchy problems, I'm going to define that the L on the right-hand side of my initial value problem, you can see there's my first order, equals some operator on X. I'm going to call it a matrix, okay? And then those are going to be the Cauchy problems I'm seeking. So it's an initial value problem of my first derivative of my function equals a matrix times the function. That is the Cauchy problem. Now, I've added two words here, homogeneous, autonomous. And what do those mean? Well, we've already talked about homogeneous, notably homogeneous saying no additive function. Okay, if I would have done like plus cosine t here or something, that's now an additive function and it's no longer homogeneous. And autonomous, we talked about in the previous section, autonomous means and L doesn't depend on time, or in other words, like L is constant in time. Okay, so autonomous, L is constant in time. Recall, we're thinking of L as matrices with regards to this book, and homogeneous meaning we're not adding a function onto the end of it. So let's scroll down to look at an example of this. We can start with a system of linear differential equations. We have an initial value problem here, right? Because x1 at 0 has an initial value and x2 has an initial value at 0. And we've calculated its first order derivative in time, and then on the right-hand side, it's equal to some linear combination of x1s and x2s. Now, why does this actually take the form of the above? Or maybe how could I write it in the form of the above? Well, we make the understanding that x1 and x2 can be considered together in a vector. Maybe I'll put some vector brackets around them. And then when I consider, well, that's not right on the right-hand side, but if I consider the left-hand side as a vector and then rewrite the right-hand side as a matrix acting on vectors, this is like x vector prime, this is like m times x vector, I can reinterpret that by just defining my vector. x1, x2, I take a derivative of that, that's like ddt of x equals a linear operator on x, L on x. But my linear operator is just the matrix that comes from the 4, 3, negative 1, 1, 4, 3, negative 1, 1 coefficients of x on the right-hand side. And moreover, I have an initial vector to negative 1. So there's my initial vector in the Cauchy problem as well. So all of a sudden, this takes the form, d dt of x equals L, right? This is my big old L, x. And then I have an initial value. There's t naught equals some x vector at 0. So that's how we can reinterpret linear differential equations as Cauchy problems. And in this case, it's a system of linear differential equations. Okay, and I make it even clearer there. Okay, so now we move on to the moving a lot. Okay. All right, now we move on to the inhomogeneous setting. So all of a sudden, I'm getting rid of homogeneity, or so-called a null space problem anymore. Now I'm going to reinterpret this as inhomogeneous because I'm adding a function onto the end. So I recovered, this is the same Cauchy problem I had before, but now I've modified it by adding a function on the end. And we just want to make sure that we know how to recognize these. Why is this still autonomous? Let's make this clear. Inhomogeneous has an additive function. Autonomous, the function is allowed to depend on time. Okay, that has nothing to do with being autonomous or not. What needs to not depend on time is L. So L does not depend on time. So that's what it means to be an inhomogeneous autonomous Cauchy problem. And if I scroll down, we can see basically I've got the same system of linear differential equations I had before, but I've modified them just a little bit by adding the additive functions t and cosine t, right? So everything else looks the same as before. My vector x1, x2 is like modified by some matrix, but I have an additive function now. That's what makes this inhomogeneous. And if I rewrite it in terms of an additive function, functions can be vector valued, right? So this is an additive vector valued function. Now all of a sudden this is behaving like L right here, this is behaving like f of t, and this is like x sub 0, and all of a sudden this is like d dt. All of a sudden it looks exactly like the Cauchy problem, right? But now we're inhomogeneous. Okay, let's move on from there. I make it a little clearer again there too if you want to look into that a little more. We basically have every single possible case here. So now I'm introducing the non-autonomous, but they are still homogeneous Cauchy problems. And all that's happened now is there's no f of t here because it's homogeneous. So there's no additive function, no plus f of t on the right-hand side. But what's special is that L, the operator, does depend on time. So non-autonomous, all of a sudden L depends on time. And homogeneous, I have no additive function. And so these are just ways of classifying. Why are they so important? Because we're going to see in the next lecture that we have different techniques for solving each one of these separately. So that's why we really want to pay attention to these. This is our non-autonomous system. And now we look at the following system. So what I've done in this system is modified the coefficients, right? The coefficients before in the autonomous systems were 4, 3, -1, and 1, but now I've modified each coefficient to now depend on time. So the coefficient here, 4t depends on time, 3 cos t depends on time, -t squared depends on time, and sine t depends on time. So if the coefficients, since the coefficients of L depend on time, this is non-autonomous. And we're going to do the same thing. I'm going to show you what L looks like, and I think a lot of you can already tell that all I do is extract the matrix, which still describes this, but now the matrix, instead of being 4, 3, -1, 1, is 4t, 3 cos t, -t squared, and sine t. And all of a sudden this matrix depends on time. So when the matrix depends on time, we're non-autonomous. And finally, our last choice, which is for obvious reasons the most complicated of all, is the inhomogeneous non-autonomous Cauchy problem. So what we're expecting here is an additive function and an additive function, and we're expecting the linear operator L depends on time. So when we have a linear operator depending on time, it's non-autonomous. When we have an additive function, it's inhomogeneous. And we see that right there. L depends on time. F is an additive function. Let's look at an example of this. So here's our system. Basically, I've just combined all of the other systems. So I have my coefficients of the linear terms, which all depend on time now, 4t, 3 cos t, t squared, and sine t. All of those depend on time. That's like L. There's my additive function, t and cos t. So I have coefficients which depend on time, and I also have an additive function. And so if I reinterpret that now with my big ol' LT is this matrix, and f of t is this vector, this is my linear Cauchy problem, which is now inhomogeneous, non-autonomous. And so today all we're thinking about is classifications. It's maybe not clear why, but we'll definitely see by the end of this chapter why we can actually rephrase every linear ODE in this form, and thus if we have a solution for this form of ODE, then we can solve all of them that are linear, of course. So that's really where we're headed in this chapter, is the linear ODE, and I make this slightly ostentatious claim that this is the only one that we really need to think of. But that's all I have. I'll see you all in class. Bye.